series. Okay, everybody should click, got it, for the recording. I want to mention that I think this is the first time that the distinguished lecturer has given lectures on different topics. This is the fourth lecture, but the first lecture was on pattern formation, and the second one was on, I guess, mathematical economics and monopolist problem. Third one was on general relativity, and this one will be on super diffusion. They're all, of course, PDE or differential equations in some form, but it's quite impressive to me that these are four very different topics. So it's the first time that's happened. So anyway, Robert McCann from University of Toronto will give his final talk. Even though it says talk 3 on the slide, it's actually talk 4. And about asymptotics for nonlinear or near extinction for nonlinear fast diffusion on a bounded domain. So thank you.
Okay. Thank you very much, Michael and Tuak and Jochen and everyone for arranging these talks. Yeah, the talk 3 is not nearly the worst error. 5 minutes ago, I realized I started from a template of some old slides of a different talk. And five minutes ago, I realized I hadn't changed the date, so it still had a 2012 date on here. So I managed to update that. So there is a version of the slides on my webpage, and I'm going to describe joint work with Byung-Jum Choi of Postech in Korea, Pohang, and Christian Seiss in Münster. And it's about the fast diffusion equation on a bounded domain. So there's going to be an introduction. I'm going to talk a little bit of the history of the problem and the goals. And hi, Suzanne. And then about the results that we get and something about the methods. So here's the equation. It's very much like the heat equation, and it's formulated on a bounded domain. And then there's this nonlinear exponent under the Laplacian M that's going to cause all the trouble. I'm going to put 0 boundary conditions on the lateral boundaries of my domain, and I'm going to put some initial data rho naught at integrable initial data rho naught at time 0. And so you can think of this equation as transporting heat from the interior of the domain omega to the boundary, and the boundary is being held at absolute 0. So eventually all the heat's going to leak out at the boundary. But there's 3 different nonlinearities that I'm going to consider. So if M is bigger than 1, then it's what's called the slow diffusion or the porous medium equation. And the porous medium equation has the property that if you had your data was compactly supported in the interior of the domain, the heat would diffuse at some finite rate, so you'd retain compact support for a while until it hit the boundary. And of course, the heat equation instantaneously spreads the heat throughout the domain, and the fast diffusion equation does that even faster in some sense. And so I'm going to be mostly focused on this, what I call the subcritical fast diffusion regime, where the nonlinear is less than 1, but bigger than dimension -2 over dimension +2. And I also require M to be positive, which is an additional constraint in case M equals 1. And one could also consider Sobolev super subcritical fast diffusion. I will have nothing to say about that. But of course, the limiting cases M equals 1 and M equals dimension -2 over dimension +2 are important and interesting cases. And especially in the case of linear diffusion, you can solve this equation more or less explicitly by separation of variables, as I'm going to recall on the next slide, because this is sort of the picture that we would like to reproduce in the nonlinear case if we could. So in the linear case, you can try to write rho as the product of a function of time tau and space y. And then if you solve the Dirichlet problem for Laplace's equation with 0 boundary conditions on your domain to get a bunch of eigenfunctions with eigenvalues lambda, you can express the general solution rho as a linear combination of these eigenfunctions weighted by exponentially decaying in time coefficients, and then the CIs would represent the initial conditions. So they'd be given by the L2 inner product of the initial data with the eigenfunction phi I. And the point is that, so first of all, the Dirichlet Laplacian is a non-negative operator on your domain, so all of the eigenvalues are non-negative. And secondly, there's a complete basis of them, a complete orthonormal basis for L2. And so I'm able to write essentially any solution in this form. And of course, but these eigenvalues live in a slightly better space than L2 because they live in the Sobolev space, whose definition is given here, and of functions that have trace 0 on the boundary. So that's the Dirichlet boundary condition coming in. And somehow we would like to reproduce this picture to whatever extent it's possible to do in these cases of the nonlinear diffusion equations. And so to provide a little motivation for the nonlinearity, let me describe models where that comes from. So, gosh, here we go. So, so of course you can write this nonlinearity in this nonlinearity here in several different ways. And the one that I want to focus on is maybe this one here, where you see that if you think of rho again as being a temperature, the temperature to the power m-1 is acting like a diffusivity. So like the rate at which the material is conducting temperature. And so if m is bigger than 1, then this diffusivity is large, where the temperature is large, it's small, where the temperature is small. And so at the boundary of a compactly supported thing, the diffusivity is going to 0. And that's why the porous medium equation retains compact support. It's also used to model things like population spreading, where rho would be a density of organisms and they're all trying to get away from each other, but they're not trying to get away. They're trying to get away from each other quickly in places where it's very overcrowded. They're not trying to move very much in places where they're alone. I'm of course interested in the opposite regime, m less than 1. So, but anyhow, let me motivate the m bigger than 1 case a little bit more. So if I think about an equation for fluid mechanics, where you'd have Newton's second law, which says something like force equals mass times acceleration, mx double dot equals f. So if I have a continuum distributed with density rho and moving with velocity v, then I apologize for using v on this slide in a different way from how I've been using it previously. But so here v is going to be a vector field instead of a, oh, I haven't used it yet. Good, fine, v is a vector field. I'm going to use it differently on the next slide, or two. So, so this is basically like the acceleration, and the applied force might be minus a pressure gradient. And if I'm moving through a porous medium, there would also be some drag associated to the medium, and b would be a coefficient of friction for moving through that medium. And usually physicists, when they have a model with friction in it, they either assume that friction is negligible. And if you do that in this equation and you couple it to the continuity equation for rho, then you get the compressible Euler system with an equation of state p depending on rho. Or they assume friction dominates. And so if you assume a friction dominates, then you might assume, say, the inertial effects are 0, and so that v would then be proportional to the pressure gradient. And if you plug that into the continuity equation, then you get a version of the porous medium equation, provided you take p to be a power of the density. So if you take the equation of the state to be this power of the density, you get the nonlinear diffusion equations we've been talking about. Other questions? Right. And so now moving on to the fast diffusion equation, what's in the fast diffusion equation, of course, this diffusivity is blowing up at low densities. It's large at low densities, it's small at high densities. And so if you have compactly supported initial data, stuff near the boundary where the density is very low immediately diffuses. Stuff where the boundary of the support immediately diffuses to the boundary of the domain. And this model was used by Berryman and Holland about 40 years ago to model plasma ions diffusing across a magnetic field with some particular value of the nonlinearity. It's also used in geometry. So I think the critical case comes up in like the Yamabe flow, for example, the case where the Sobolev critical case. Now, of course, a feature of the fast diffusion equation is that because low densities diffuse quickly, unlike the heat equation where you have to wait for infinity until time goes to infinity for all these modes to decay exponentially to 0. For the fast diffusion equation, there's going to be some finite time after which rho is identically 0. And I'm interested in the rate at which this convergence to 0 happens, and also in more subtle details about how the convergence to 0 happens. So higher asymptotics. And so Berryman and Holland, who I say were trying to model these plasma ions in a magnetic field, they observed that if you do a change, you can rescale this equation. So if you expect rho to vanish at time capital T, you can divide by t minus the time tau. And if you raise that to the appropriate exponent, you will find that this thing tends to a fixed point. And in fact, if you also rescale tau, so if you replace tau by some t that's going to infinity when tau goes to capital T, then you find that okay, you have to also raise rho to the power m, or equivalently take the mth root of v. So let me introduce this exponent p, which is 1 over m. So v is going to satisfy this dynamics if and only if the associated rho satisfies the dynamics that we're interested in. So from now on, I'm going to consider this equation for v. And notice that the right-hand side of this equation is actually the variational derivative of a nice energy, so that variational methods are going to be useful for me in trying to treat this problem. This, I guess, Berryman and Holland observed that there was an energy dissipated by this flow 45 years ago. And here's the energy. It's basically the Dirichlet energy minus a nonlinearity. And this is exactly when m is bigger than dimension minus 2 over dimension plus 2. The Galliardo-Nurnberg-Sobolev inequality says that this nonlinearity will be controlled by this energy, and so the E will be bounded below in that case. And I think maybe okay, maybe E is not bounded below, but there's at least enough compactness in the problem for Bourget to show that there are going to be some fixed points of the dynamics that are positive. So we're interested in non-negative initial data, and the non-negativity is preserved by the evolution, basically by the maximum principle. And so again, 45 years ago, Bourget shows that there are stationary states for the dynamics I'm interested in. And Berryman and Holland a few years later show that at least along subsequences, as time goes to infinity in the rescaled variables, you're going to get one of these positive stationary states. And they conjectured that that the stationary state would actually be unique, and moreover, in one dimension they gave some conjectures about higher order asymptotics. A few years later, Brzezis and Nurnberg showed that for certain domains, depending on the domain geometry, you can have situations where there's multiple positive solutions with the Dirichlet boundary conditions. So in particular, if you look at a thin annulus, you can have multiple solutions. On the other hand, if your domain is the ball, Gitas Nurnberg, 10 years earlier, had shown that there was a unique positive stationary state. And so the domain, and then since that time, there a lot of different authors have looked at the effects of domain geometry on the uniqueness or non-uniqueness of positive solutions to these problems, to these stationary problems. Okay. About 20 years after the work of Berryman and Holland, Feiereisel and Simondon were finally able to show that not only is the evolution converging along subsequences in time, but in fact, all subsequences converge to the same limit, but the limit depends on the initial condition where you started. And a decade after that, Bonfort, Guyot, and Vasquez showed if you take your solution and you divide it by the thing that it's converging to, then in the L infinity norm, with so-called the relative L infinity norm, this ratio is going to tend to 1. And if m was close to 1, they were able to show that this convergence is exponentially fast. And recently, there's a preprint out by Jin and Xiang, which gives a polynomial lower bound on this rate of convergence. And there's also a paper that just appeared due to Bonfort and Fagali, which actually inspired our work. And it says that usually this convergence is exponentially fast. Well, maybe not usually, but what they show is that it's exponentially fast for most domains. So for a C2 alpha dense set of domains, you get this exponential rate of convergence. And so that was very intriguing for us because we wondered why they needed the domain to be generic, to be C2 alpha generic. And a new proof of their result appeared in a preprint last year by Akaji, who uses, so they do this using an entropy method, entropy dissipation method, and they introduce some what they call almost orthogonality relations in order to get this. And Akaji has a simpler proof based on energetic rather than entropic methods. Okay, questions? So basically, my talk today is going to be about trying to close the gap between this polynomial lower bound on the rate of this convergence and this exponential upper bound that holds on most domains. So let me describe a little bit how our approach, which is going to be a linearization approach. So we don't use entropy or energy methods, and at least not the same way that Bonfort, Fagali, and Akaji use them.
Question: all this in bounded domain, right?
All of this is in a bounded domain with Dirichlet lateral boundary conditions and some non-zero integrable initial condition.
Is there any other phenomena in unbounded domain? Like in,
Yeah, so in unbounded domains, I mean, so Jochen and I worked a lot on this problem on the whole space. And in the whole space, these equations conserve mass, at least if M is not too small. And so, for example, the heat equation conserves mass, but it takes any initial condition, it spreads it out at rate square root of t, square root of tau. And the longer you wait, the more and more the solution looks like a Gaussian. And you can then try to quantify the rate at which it converges to a Gaussian as it spreads, and also the rate at which it forgets aspects of more subtle aspects of the initial data. And I was actually going to talk about this a little later, but so if you view the picture from distance square root of t, then you'll see it converging to a standard normal Gaussian. And that's where you would try to, that would be analogous to the transformation that I showed you a minute ago from rho to v. And if you go to the porous medium regime, instead of converting to a Gaussian, it converges to like a spreading droplet of compact support, where the exact power of m determines the Holder exponent of continuity for the support. And if you do the fast diffusion regime, then instead of a Gaussian, because things at low densities diffuse very quickly, it develops thick tails. So it converges to what's called a Barenblatt solution. So, you know, it looks like this, but instead of the tails being Gaussianly small, they're algebraically large. And so you only have a finite number of moments in that case. Does that answer your question?
Yeah, thank you.
Okay. Okay, so we're going to look at the our solution relative to its long time limit. If we subtract 1 for that, we know that H is converging uniformly to 0. We can also write a dynamics for H. And so I'm going to separate out the linear part of the dynamics from the nonlinear part of the dynamics. So the linear operator here takes the following form. And it's maybe nicer to write it in this way, which shows you that this is still a positive operator. And so this is always bigger than 1 minus p. So this 1 minus p is going to be a lower bound for the spectrum, but it's, so p is 1 over m here. So it's a negative lower bound for the spectrum. And then the nonlinear part of the operator, so the red part here you can see is like by binomial expansion, you see it's something like h squared in lower order terms. The blue part is something like, so this is, this we said was order h squared. The blue part is order h, but it's being multiplied by this, an additional factor of h. So this thing is sort of quadratic plus lower order corrections, quadratic in h plus h cubed terms. But the nonlinear depends on derivatives of h as well as h. Now, for solutions of this equation, you can also write the nonlinear in this form m of v, where basically you can trade the space derivative for 2 time derivatives if you want. So it's parabolic scaling. So the blue form of the equation is, I guess, semi-linear because the highest order term is here. The red form is maybe quasi-linear because these 2 space derivatives are getting multiplied by non-linearities in h. And we use both the blue and the red form of the equation in our analysis. So of course, if you to learn much from this linearization, you need to know you need to diagonalize the linear operator, and you also need to control the nonlinear operator. And basically, diagonalizing the linear operator is essentially what Bonfort and Figali did, and they work in these weighted Hilbert spaces. So I'm going to always be looking at a weight exponent r of whatever stationary solution I'm converging to. And for me, I think Q is always going to be 2, so I'll always be in a Hilbert space, and here's the inner product in that Hilbert space. And the observation is that the linear operator that we just wrote down, especially if you look at this form of it, you can see that if you multiply this by v to the power p plus 1, you can then integrate by parts, and so it will be a symmetric operator. So it's if you choose the weight to be p plus 1, then your LV is actually a self-adjoint operator. And moreover, it turns out to have a complete basis of eigenvectors. And the eigenvectors can also be seen as critical points for this kind of weighted Dirichlet energy on the LP unit sphere. And the boundary condition is not that the eigenfunction vanishes, but rather the eigenfunction times v vanishes. And basically, in some sense, the way Bonfort and Figali prove this, they don't actually work on this weighted space. They work on this space here. So the weight is a little bit smaller. But multiplication by v inverse is a unitary isometry between this weight and the weight that we want to work with. And they show that when you compose with this unitary isometry and its inverse, and if you add enough to the function, remember I said LV was bounded below by 1 minus p. So if you add p to this function, you're bigger than the identity. And so this guy has a compact inverse, and they can apply the Riesz-Schauder theorem to get a complete basis of eigenfunctions. That's more or less how the diagonalization goes. But as I was mentioning, the eigenvalues are not all going to be non-negative. So I want to index them the following way. So I'm going to suppose that there are I negative eigenvalues, and there's the possibility of some k zero modes. And so so I'm going to call the smallest eigenvalue lambda minus I. They're going to count up to lambda minus 1. There may or may not be zero modes, and the first non-zero mode will be lambda k. So it would be lambda 0 if there are no zero modes. It'll be lambda positive otherwise. Lambda k, right? And in fact, lambda k, the first non-zero eigenvalue, is the exponential rate that Bonfort and Figali were able to show under this genericity condition on the domain. And actually, because of this lower bound on the linear operator, you can check that the eigenfunction 1 is an eigenfunction that attains that lower bound, and it's the only such eigenfunction. So the smallest eigenvalue is simple. It's not clear whether there are any other negative eigenvalues. And more or less, the smallest eigenvalue arises because of time translation symmetry in the original variables. So in other words, the capital T that I use to move from the rho variables to the v variables, if I delay rho a little bit, it's going to vanish at a different time, and I need to divide by a different capital T. And that's if I divide by the wrong capital T, things are not going to converge nicely, and so I get this very unstable instability due to that. There may be other instabilities. There may be neutral modes. These are the positive modes. So more or less philosophically, Bonfort and Figali's convergence result is very plausible because you already knew that things were converging from Feirazel and Simondon. So you know that these negative nodes, if they're present, are not active somehow. And Bonfort and Figali were not able to accommodate the possibility of zero modes, but they appealed to a 40-year-old result of Sota and Tamam that said, on a generic domain, there will be no zero modes. So if there are zero modes, it's sort of an accident of the domain geometry. And so more or less, that's how they get the result. And as I said, I'd like to close the gap between their exponential convergence and Jin Xiang's algebraic lower bound, exponential upper bound, and algebraic lower bound. If possible, we'd like to access higher ordered asymptotics, such as those conjectured in one dimension by Berryman and Holland. And finally, we'd like to understand better to what extent the presence of zero modes spoils exponential convergence. Any questions? Okay, so that's the agenda. Here's the result, the first result. So suppose I have a solution to the dynamics, and I know when I divide it by V that I've chosen the correct V, the correct ground state, such that the relative error tends to 1 uniformly. Then I say there exist constants C and epsilon that depend on the nonlinearity in V. And some lambda, which you can take to be lambda k if you like, but you may also be able to take it to be bigger, such that as long as the solution is less than epsilon, is uniformly less than epsilon, the relative error is uniformly less than epsilon for all time. And we know it will eventually be less than epsilon because of Bonfort, Grillo, and Vasquez results. So just translate times up, make the starting time large enough that h is less than epsilon. Then either one of two things holds. I call them 4 and 5, although they could have been called 1 and 2. So either both this weighted Hilbert norm and the L infinity norm are decaying slower than 1 over t for large times, or both the L infinity norm and this Hilbert space norm on the relative error are decaying exponentially, where lambda is again at least the spectral gap. And the exponential bound holds for all times bigger than 1. So that's the first dichotomy. Either you're converging slower than 1 over t, or you're converging faster than exponential, where this is the spectral gap, and we don't care whether zero modes are pleasant or not. And in the second case, when 5 holds, you can actually say more than this. So you can hope, if things are decaying at rate lambda of t, because the nonlinearity is quadratic, you can hope to get asymptotics relatively easily up to order 2 lambda of t. And so if 2 lambda of t lies between the jth and the j plus first eigenvalue, then I can find constants depending on the initial data, such that if I subtract off multiples of those first j eigenvalues weighted by decaying exponentials decaying at the rate of their eigenvalues, I get this faster rate of convergence. And there, I put this red t in here. This red t is only present if 2 lambda equals the upper endpoint of this interval. So in other words, this red t is a resonance effect that comes if I want to choose a threshold 2 lambda that's equal to the upper endpoint of this interval. So in some sense, this result helps to close the gap between Jin and Xiang and Figali and Bonfort. And it also shows that zero modes are not really hurting you, unless they push you into this first alternative. And secondly, this is showing, at least to this limited extent, it's showing the higher order asymptotics that were conjectured by Berryman and Holland 45 years ago. All right. So I guess there's a lot to digest on this page, and maybe there might be questions.
Sorry, K, the zero eigenvalue mod or the first positive one? Sorry, I forgot that.
K, lambda K is the first positive one.
First positive. Okay.
Yep. Thanks. Yeah, that's important. And so then we have another dichotomy which says, in some cases, we can say you're in the second alternative, that you're not in the first alternative, even in the presence of zero modes. And so, for example, so I mentioned one of the situations in which you can get non-unique ground states. You take a thin annulus. It turns out that you can find a ground state which is not rotationally symmetric. And so then every rotation of that ground state is also a ground state. And which one do you converge to? It's hard to tell from your initial data, but you're going to converge to one of them. And in some sense, the other ones don't really matter. There'll be zero modes associated with those other ground states, but they don't really affect the rate of convergence. And so here's our next theorem, which tries to capture that idea. So let me look at all fixed points in the dynamics.
So may I ask a question? The
Yeah,
previous,
sure.
the result, can you? So it looks like for the exponential, it's the negative eigenvalues that are responsible, right? If you subtract out some, I don't know, some combination of the negative, the exponential with the negative exponents, will you still get like some sort of, with a t decay?
Yeah, so wait a second. So there's a sign, I'm a little confused about what you mean by the negative eigenvalue. There are, in principle, there are unstable modes, and there are stable modes, and there are neutral modes. And we all, by Feirazel and Simondon's result, we already know that the H is converging to zero uniformly. And so that tells us that the unstable modes can't be present, can't be active. Although the unstable modes are there in the linearization, they have no effect on the nonlinear dynamics.
I see.
Okay.
Okay.
Right. The neutral modes may or may not have an effect on the nonlinear dynamics. Right. Were there any other questions? Okay. So so now in my second dichotomy tries to address when do the neutral modes affect when can the neutral modes ruin the exponential rate of convergence. So I'm going to look at fixed points V in the Sobolev space, which are fixed points for the dynamics. I mean, a priori, they could be weak solutions, but it turns out they're actually, they go to zero at the boundary, but in the interior, they're even to the boundary, they're Holder 3 times differentiable. They're maybe not more than Holder 3 times differentiable, depending on what nonlinear you've chosen. So the set of V, which are fixed points for the dynamic, capital B's, in other words, they belong in this Holder space. And we are also able to check that they all look like, so V is basically proportional. It's bounded above and below by constants times the distance to the boundary of omega. So because of this being bounded above and below by constant times the distance to the boundary, the ratio of any V and W is going to be, sorry, I should have said fixed points V non-negative for the dynamics. I'm only interested in non-negative solutions here. So the ratio between V and W is going to be a bounded function. And so I look at the set of all these fixed non-negative solutions to the dynamics, and I want to put a topology on that set. And so it's natural to want to try to use this kind of relative uniform topology, which is of course not symmetrical in V and W. So it's not a metric, but nevertheless, I can take these sort of balls to be a base for a topology. And I'm going to call one of these non-negative fixed points an ordinary limit if and only if the set of fixed points nearby forms a manifold whose dimension agrees with the number of zero modes, so with the dimension of the kernel of the linearization. And I'm moreover going to assume that when I represent a solution W by the ratio W over V, that is a differentiable embedding of this manifold S into the Hilbert space where I'm studying the dynamics of H. And then my second theorem says that if V is an ordinary limit in this sense, then the convergence is exponentially fast. So in other words, if the big thing, I guess the take-home message is if the manifold of solutions nearby agrees with the nullity of the linearization, if the dimension of the manifold agrees with the dimension of the nullity of the linearization, then you still get exponential convergence. And so we could guess maybe that's the case on these annuluses, where in 2 dimensions, we know there's a non-rotationally symmetric solution on the annulus, so there has to be a 1-parameter family of ground states. If the dimension of the kernel is 1, we still get exponential convergence. That's what this theorem is telling us. Questions? And I have to say that this theorem is very much inspired by work from the 80s in the area of minimal surfaces and curvature-driven flows by Almgren, Allard, and Simon. And they don't use, so ordinary limit is our term, but they say basically that a tangent vector is integrable, a tangent vector to the set of solutions is integrable if there's, sorry, I didn't get it quite right. A zero mode is integrable if it's a tangent vector to the set of solutions. And I have to say that our intuition is that ordinary limits are in some sense generic, and I can sort of tell you why. The basis for our intuition is that the set of solutions is kind of like you're trying to solve some PDE, but imagine that it was, and it's sort of analytic. So imagine that you were trying to solve a polynomial equation or an analytic equation for a finite dimensional space instead of an infinite dimensional space. Then S would be an analytic variety. And so that means, of course, it could have parts of its zeros, which are like 1-dimensional, and parts of its zero set, which are 2-dimensional, and they can intersect. And so at a point like this, so here, out here, S is a manifold. On here, it's S is a manifold. They're manifolds of different dimensions. At a place where they intersect, this would be like the variety, maybe Z times X squared plus Y squared equals 0. At this place where, maybe I got it backwards. Maybe this is the variety X, Y times, oh gosh, let me not try to say what variety it is. Where they intersect, you know, it's not a manifold anymore, but there are null vectors associated with the horizontal vectors, and there's a null mode associated with the vertical vectors. So the kernel in this case is sort of 3-dimensional, but the dimension of the manifold doesn't agree with it. So points like this, singularities of analytic varieties, are small, at least in finite dimensional spaces, and we suppose they're also small in the PDE sense. And the other thing that can go wrong is that, so that's somehow this question of whether S is a manifold or not near V. And we expect that generically S is a manifold near V, except at bad points like this. And the other way that a point could be ordinary is that the dimension of the manifold might be larger or smaller rather than the dimension of the null space of the linear operator, like as happened when you had just a single point, when S was a single point, but for accidental reasons you had a bunch of zero modes. But Sout and Tamam say that's very unlikely. You can sort of, if you perturb it a little bit, the zero modes will go away. And so we sort of expect the same thing with our S's. If you, it's very unlikely that you have zero modes beyond those that are forced on you because they're tangent vectors to the set space of solutions. All right, so we have a conjecture. That's our conjecture. but we don't know how to make more precise what this conjecture is. So anyhow, we expect that exponential convergence is very generic, and slow convergence like 1/t is we know that it applies only to non-ordinary limits. Okay, so before I talk more about proving the theorems, I wanted to tell you a little bit of the history of the case where you do the whole space problem instead of the bounded domain problem. And I invoked that case a little bit in response to Tuak's question earlier on. So in that case, 50 years ago, Friedman and Kameen showed that as long as, oh yeah, and it's in this case, of course, the fast diffusion equation has these algebraic tails. Only q moments can be, the thickness of the tail is such that you can only integrate q powers of y against the tail. So Friedman and Kameen showed 50 years ago that if you take any two solutions with the same total mass, let's say non-negative solutions, then the dynamics is acting like an L1 contraction. It's getting smaller as tau increases. Three groups of authors at about the same time, around 2000, showed that if m is smaller than a slightly larger exponent, this is something like 1 minus 1 over the dimension, m0 is something like 1 minus 1 over 2 over the dimension, that you can quantify the rate of contraction, and there's some exponent that depends on exactly what nonlinearity you're dealing with. Carrillo and Vázquez showed that if you restrict your attention to radially symmetric initial data, you can improve the rate of convergence. Jochen and I showed that we sort of linearized the problem. We rescaled and linearized, and were able to find the spectrum. Vázquez showed that now I'm in the fast diffusion regime. If you look at this relative error again between two solutions, that will go to 0 as time goes to infinity. And eventually, okay, so the other authors made some contributions, including me with Yongjung Kim, but eventually with Koch and Densler, about 10 years ago, although it took a while for the paper to appear, we were able to show that the spectrum that we had found earlier we were able to get this rate for all centered initial data. So you don't really need radial symmetry, you just need the center of masses to be in the same place. And then we were able to capture higher order asymptotics up to, I think, the square of this rate. And okay, not the higher order asymptotics, but the rate was obtained by other authors at about the same time. And the analogous linearization in the case of the porous medium equation in one dimension is old, was done by Barenblatt. In higher dimensions was done by Christian Seiss during the time he was a postdoctoral fellow with me in Toronto 5 or 6 years, or 10 years ago, maybe by now. And after he left Toronto, Seiss actually developed an invariant manifold theory, which actually goes beyond the square of this rate to understand how the dynamics evolve in great generality. For the porous medium case, in dimension greater than 1, in one dimension, and sort of invariant manifold theory had been written down by Angenant already in 1988. All right, so that's the history of this problem on unbounded domains. But there's a caricature from that is useful to recall here, which is that if I was studying a finite dimensional dynamics given by some vector field f, and I want to linearize it around some fixed point, what I would expect is that the derivative of f predicts the leading order behavior, and then there will be quadratic corrections, at least if the fixed point is attractive. So if the spectrum of f is all non-negative, and I have some eigenvectors associated to these eigenvalues, I would expect to leading order the distance to the fixed point to be going down like these exponentially decaying factors times the eigenfunctions times the constants that tell you what initial data you started with. And then the corrections, because the nonlinearity is smooth enough, are going to be of the form products of this stuff. So the first correction is going to occur at lambda 1 plus lambda 1, which is order 2 lambda 1. And so the point of being able to double the rate is that up to double the rate, you can ignore these higher order effects of the nonlinearity. If you want to penetrate further into the spectrum than this, you have to start taking these terms into account. And the other story in the whole space problem was one of the big technical challenges for us was showing in order to do this kind of linearization, you need to know that the vector field is depending differentiably on the initial condition. You want to be able to linearize the vector field around x infinity. And so a lot of technique was invested in showing this differentiability. So how is the situation on bounded domains different from this? So first of all, on bounded domains, we have to cope with these unstable and zero modes. which we didn't have to deal with in the unbounded case. And secondly, we have to not estimate the nonlinearity in a rather different way. But the good news is that in the unbounded domain case, there were a lot of problems associated with the fact that the spaces in which we could estimate the nonlinearity quadratically were not the same spaces in which we could diagonalize the linear operator. And so that was sort of a technical nightmare for us. In this case, it turns out that the estimates work beautifully in this Hilbert space. Now, you remember the nonlinear operator involved v times either v or its time derivative. So that's a nice quadratic estimate. But in order to make Hilbert space techniques work, we really like the nonlinearity in the Hilbert space to be estimated by the square of the solution in the Hilbert space. And we're not able to get that. But what we are able to get is, because it's parabolically smoothing, if you wait a little while, so if you wait time 1, then because of the parabolic smoothing, you can sort of estimate this L infinity norm now in terms of what the LP norm was 1 unit of time ago. And so we kind of get this sort of delay differential equation type of estimate for the nonlinearity. And so once we have this, then basically that says up to quadratic corrections, we're in either one of these model cases. So 1 or 2. 2 is the case where you have a bunch of modes evolving at rate lambda, bigger than some lower bound, and then they're non-linearly coupled together, but you have a quadratic estimate for the nonlinearity. And that's good news as long as you're close enough to 0, then you can use Gronwall's inequality to estimate, to replace this set of equalities by a set of differential inequalities that tell you how fast the magnitude of x can grow. And it turns out it can't grow very quickly at all. In fact, the magnitude of x at time t squared is controlled by the original magnitude of x plus this exponential penalty. And the rate is not quite lambda because there's a little error that depends on this k here and the epsilon. But if once you have this estimate, if you go through the argument again using this better bound than what you had initially, you can finally obtain a kind of growth estimate like this, where you can absorb the extra error into the constant in some sense and get exponential convergence at sharp rate lambda. So that's case 2, more or less, once you have this kind of quadratic estimate, and if you didn't have the -1 here. And case 1 is that the neutral mode dominates, so that a dot is proportional to a squared, and then if you neglect higher order corrections, it might be a cubed or whatever, and you integrate this without the higher order corrections, you get decay at rate 1 over t. If c was 0, so the leading order correction was a cubed, you get decay at rate 1 over t to I guess slower decay, so a smaller power. Okay, so somehow we want to show one of these 2 model cases holds. Okay, so I'm going to tell you a tiny bit about how we cope with the unstable and 0 modes, and then a tiny bit about how we cope with the nonlinearity. So for the unstable and 0 modes, we use this technology which goes back to, there's a famous ODE lemma of Merrill and Zag, which actually has its roots in work a little bit earlier by Philippus and Cohn. And I think of it as being a kind of dominant balance. But we actually need some quantitative refinements of this Merrill-Zag lemma. And the quantitative refinements are mostly due to Kyung-Soo Choi and collaborators. So here's one of them. So Choi, Hasselhofer, and Herskovitz in a preprint from 4 or 5 years back show that suppose you now have 3 non-negative quantities, x, y, and z, absolutely continuous on the positive reals, and they satisfy a system of ordinary differential inequalities. And so the first one says that x is trying to grow with rate 1. And the last one says that z is trying to decay with rate 1. And the middle one says y is not trying to do much of anything. And apart from this growth and decay, there's some coupling between the modes, but the coupling is suppressed by a constant epsilon, which is small, at least after time capital S. And then the Merrill-Zag lemma, or this quantitative refinement of the Merrill-Zag lemma, says, if you know that the sum of these 3 non-negative quantities tends to 0 in the long time limit, first of all, the unstable quantity, the quantity that's trying to grow, has to be controlled by the stable quantities, because otherwise you wouldn't get decay to 0, you would get blow up. And secondly, at least for the times in which the estimates hold. And secondly, you can't have all 3 of these things going to 0 at the same rate. 2 of them are going to 0 faster than the other one. So either y is going to 0 the slowest and x plus z are going to 0 faster as s goes to infinity, or z is going to 0 the slowest and x plus y are suppressed by a factor epsilon relative to z. And that doesn't, you don't need the large time limit that for that. You get that for all s bigger than s, all s such that the estimates hold. So the moral of the Merle-Zag lemma is that only the rate is determined by one of these three quantities, not any interaction between them. And that's the dichotomy in our first theorem. Either the stable modes are dominating and things are going to 0 exponentially at the rate of the spectral gap, or the neutral modes are dominating and things are going to 0 like the neutral modes, which is like 1 over t. So this ODE lemma drives the analysis. The precise form of the estimates I stated depend on having this precise quantitative refinement of the ODE lemma. And the nonlinear, so we also need to estimate the nonlinearity, and here's the estimate that does that. So we were willing to assume that our initial data was uniformly small, and that didn't cost us any generality because of Bonfort-Gurion-Vapka's result from 2012. Under that assumption, parabolic smoothing and delicate control near the boundary using this kind of linear growth of the ground state allows us to estimate any number of time derivatives uniformly in terms of the data at a slightly earlier time, in terms of the Hilbert space norm of the data at the earlier time. And I have to say that there are estimates by Jin and Shang for that give regularity even up to the boundary of this equation. I think there's another preprint more recently than that. I can't remember when. But unfortunately, the smoothing estimates of Jin and Shang were not quantitative. So they said maybe the solution's smooth, but they don't say how the norm depends on the data. And we need quantitative versions in order to make our analysis go through. So we sort of had to redo this regularity theory, getting out quantitative versions. Okay, so I'm almost out of time. I have one more. So we have one more quantitative refinement of the Merle-Zag lemma that we needed in order to get the second dichotomy result, the one that said, if the dimension of the set of stationary solutions agrees with the dimension of the kernel, then you get exponential convergence. And here is that. That's also a refinement due to Kyung-Soo Choi and Li-Ming Sun, again, in a preprint from a couple of years ago. It's sort of the same setting of the previous theorem. We have these three absolutely continuous non-negative quantities. Suppose they're small on some large interval in time. And x is trying to grow at rate lambda, z is trying to decay at rate lambda, y is not trying to do anything except through its coupling to x, y, and z. So I guess the epsilon from the previous slide is like sigma over lambda from this slide. If I have these inequalities on a large interval in time from minus L to capital L, then on half the interval, I can make a quantitative statement that says both the growing mode and the decaying mode are controlled by the neutral mode plus a little error. And the error is controlled by how big these three things are, and the length of the interval suppressed by the rate of growth and decay. So we needed this refinement in order to show the second corollary, which is the one that says, if the dimension of the set of solutions agrees with the kernel, then you get exponential convergence again. And so I think that my time is basically up and I don't have too much more to say. So I'd like to thank you very much for your attention.
Thank you very much. There's been some questions during the talk, but let's see if there are additional questions